Well, hello everyone to this month's Climate Change, Ag, and Water webinar. I am Juan Sesmero with Purdue University Extension, and the session for today is entitled The Effect of Climate Change on the Economics of Conservation Tillage, a study based on experimental data in Indiana. Before we begin, I would like to formally welcome everyone to the webinar. I'd also like to mention that this webinar has been made possible by a grant from the North Central Region Water Network. The coordinating team for these webinars is myself, Laura Edwards and Dennis Tody with South Dakota State University, Tyler Williams with the University of Nebraska-Lincoln, and Peter Tomlinson with Kansas State University. If you have any questions at any point during the meeting today, don't hesitate to type those into the chat box or the Q&A box. If you would like to ask a question personally with your microphone, please let me know via the chat or Q&A box so that I can unmute your line. With that said, I will provide an introduction for our speaker. Dr. Juan Sesmero is an assistant professor in the Department of Agricultural Economics at Purdue University. He completed his PhD at the University of Nebraska-Lincoln. His teaching and research activities are focused primarily on natural resource and environmental economics. He has a strong interest in the identification and measurement of trade-offs between economic efficiency and distributional equity in the context of energy, climate, and water policy. So without further ado, I would love you to take over, Dr. Sesmero.
Okay, great. Thank you very much. I'm trying to share my screen here with everybody, so please let me know if you can see it right now.
Yes.
Okay, great. So thank you very much for the introduction. I'm really happy to be here. I think these are very relevant topics, and I'm excited to share the results of our research with you. So basically what motivated this research is the fact that the scientific literature has, although it has paid a lot of attention to the cost and benefits of conservation tillage and the attractiveness of tillage for farmers, there's a dearth of information, specifically in terms of how crop yields respond to different tillage practices, and how weather shape those yield responses. And so basically, the main motivation for this is we know that to a great extent, or a key factor in adoption of conservation tillage is the effect of conservation tillage on the farmer's bottom line, is on the economics of crop farming. And so we know that to a great extent that depends on differences in crop yields under different tillage practices, and we also know that those differences depend or are to a great extent determined by weather. Now, in addition to all of that, we also know that weather is changing over time, and climatic patterns are changing over time. And so it seems obvious to ask the question, what will happen to, so what's going on with the economics of conservation tillage today, and what will happen to that economics as climate patterns evolve and change due to climate change? A key component of that analysis is to actually quantitatively estimate the effect of conservation tillage on yield. And so what we did, and by we, I mean a student of mine, a smart student of mine, Whitney Hadi, here in the Ag Econ department, and my colleagues Ben Gramick and Otto Doring in Ag Econ, and Dr. Tony Vine from the agronomy department here at Purdue, So basically, we set up to determine or to examine the economics of alternative tillage practices under current and future climate, because we realize that there's a pretty big gap in the literature on this issue. And so before I start talking about the details of the study, I would like to start by defining conservation tillage. And in fact, in general, how people and how the literature has defined conservation tillage is practices under which 30% or more of the residue stays on the soil between harvest and planting, which is the critical erosion period. Now, this could be achieved through a number of different implements like chisel plow, which requires just one pass, or no-till, where soil is left mostly undisturbed. And in fact, we will examine three specific types of practices: moldboard plow, and then conservation tillage. In conservation tillage, we'll consider chisel till and or chisel plow and no-till. Those are the three practices that we're going to be comparing today. So why is it so important to analyze the economics of conservation tillage, and why do we care about adoption or potential adoption of conservation tillage? So for the most part, we know that conservation tillage has what we call external benefits, and that is benefits that are beyond the farming operation. So adopting conservation tillage tends to reduce, and there's accumulated evidence, especially in the agronomy literature, tends to reduce soil erosion and transport of sediment and nutrients to water bodies, and that in turn reduces damages to water quality, so basically reduces water pollution. Water pollution, of course, has adverse effects on ecosystem services. And so there's a water quality benefit to adoption of conservation tillage, although those benefits are sometimes very hard to quantify. In general, that's what the evidence suggests. And also there's a greenhouse gas emission reduction effect, as adoption of conservation tillage allows more carbon to be stored in the soil. And so given those external benefits of adoption of conservation tillage, and given that a lot of those benefits are not actually accrued by farmers, there could be a misalignment between societal cost and benefits of conservation tillage and private cost and benefits of conservation tillage. Now, of course, the adoption of conservation tillage to a great extent depends on, as I said before, the effect of conservation tillage on the farmer's bottom line. And so, does adoption of conservation tillage increase or reduce farmers' profits? That is not the only, clearly not the only factor in adoption of conservation tillage, but it's a very important one, and we need to understand what is it exactly. And so conservation tillage could affect farmers' profits through many channels, but particularly the most important ones are, one, yield response, which we'll focus on in a minute, and then of course also cost. Tillage operations involve costs that need to be paid by the farmers, and so conservation tillage alternatives tend to reduce costs because it reduces expenses related to equipment, passes, labor, fuel, and things like that. And so between cost savings associated with conservation tillage and its effects on yield, the combination of both will determine whether conservation tillage is preferable by the farmer or not, and in this study we'll actually try to quantify those effects. Of course, if conservation tillage happens to be more profitable than conventional till, then social incentives and private incentives are aligned, and there's not really a case for policy intervention. But if conservation tillage is less profitable than conventional tillage, then there could be a misalignment between social and private incentives, and there could be a case then for policy intervention. This chart basically shows or portrays the evolution of adoption of conservation tillage in Indiana. And as you can see, adoption has been going up especially over the 90s, and then kind of stabilizes after the 2000s. And you can see how it varies also by crop. So adoption of conservation tillage tends to be higher for soybeans than it is for corn, and our later analysis will reveal some of the mechanisms behind this stylized facts. But one thing that we can take out of this figure is that after the 2000s, adoption of conservation tillage has kind of stabilized and hasn't increased that much, and it has been higher for soybean than it has been for corn. So adoption of conservation tillage has changed over time. Now, this other graph shows that adoption of conservation tillage has also is also spatially heterogeneous. Doesn't only change over time, but also over space. What you see here in Indiana is darker colors. So the graph on the left, that's adoption of no-till specifically for corn. And then on the right-hand side, you have adoption of no-till for soybeans. Whenever you see a dark color, that means that adoption is higher. Adoption of no-till, it's higher in the sense of a higher percentage of agricultural land is operated under no-till. So the one pattern that we can take out of these figures is that adoption is higher in the south of the state for the most part, and this reveals something that the agronomy, or is consistent with something the agronomy literature has suggested repeatedly about the benefits of no-till. So in areas that are typically warmer and drier, conservation tillage tends to perform better, and so it's more likely that farmers will adopt conservation tillage. So these figures seem to suggest, are consistent with the agronomic evidence. It also seems to suggest that farmers do care about the economic performance of alternative conservation or alternative tillage practices before they take the plunge and adopt conservation tillage. So as I said before, if we know that weather matters for the economics of conservation tillage, and in particular for the differences in yields under alternative tillage practices, and if we know that that weather is changing over time, then it seems obvious to ask the question, what will happen to the economics of conservation tillage as climate change kicks in, and as a result, what is going to be the link between climate change and to an extent water pollution? So for example, if climate change improves the economics of conservation tillage, that means that there's going to be potentially a reduction in soil erosion and an improvement in water quality, which means that climate change is negatively correlated with water pollution. But if the opposite happens and climate change actually adversely impacts the economics of conservation tillage, then there's a big problem, because that means that climate change will probably be positively correlated with water pollution. So we will have two mutually intensifying environmental problems. So what this slide basic model overview describes is basically the general research strategy of our study. So what we do is we used, one of the reasons why there's a gap in the literature regarding how conservation tillage combines with weather patterns to determine the relative economics of different tillage practices, is that we don't have enough, we need to estimate yield responses to different tillage practices and how weather shapes those responses. And in order for us to do that, you need data on crop yields and under different tillage practices, and with a data set large enough to estimate those things, and of course combine everything with weather information. So fortunately, we do have something like that here at Purdue, because we have this tillage plot experiments that have been going on for 40 years now. So we use those experiments and that experimental data to actually estimate the effects of tillage and weather on yield. And that yield estimation is the basis for our entire analysis. It's what allows us to simulate yield responses under current weather conditions, but also what allows us to simulate yield responses to future weather conditions under alternative tillage practices. Without that yield function estimation, there's no way that one can simulate the effects of climate change on yield and on the economics of conservation tillage. So that's the key contribution of this paper, is the fact that it uses a long-term experiment to estimate the yield function that then allows us to analyze the economics of conservation tillage under current and future weather. So once we estimate the yield function, we combine it with random weather observations, and then also with crop prices and tillage cost information, and to obtain what we call the probability distribution of net returns from tillage. So I will show you in a second a graph that I think better portrays that. But once we obtain those probability distributions, we can compare alternative tillage practices, incorporated into the analysis the uncertainty and the risk that is associated with weather. So to give you an example, let me go back to the previous slide. To give you an example of what I'm referring to here, the agronomic literature has suggested over time that, as I said before, conservation tillage performs better under warm and dry weather. So in every growing season, there's a certain probability that weather will be warm and will be dry, and there's a certain probability that weather will be cool and wet. And so what this yield function allows us to do is to simulate weather, combine it with the yield function, and then that will give you a net return, a probability distribution of net returns under conservation tillage and under conventional till. And so what we can then determine based on that is, for example, what is the probability, considering risk and uncertainty on weather, what is the probability that no-till will result in higher profits than, say, chisel till? And then what is the probability that chisel till will result in higher profit than moldboard plow? And so we can compare these tillage practices not on a binary world in which we say, well, this practice is better than this other one, but in a more realistic random world in which we determine really how likely conservation tillage is to perform better than moldboard plow. And then we ask the question, well, after climate change, how does that probability change? So is climate change making conservation tillage more likely to perform better than moldboard plow, or less likely to perform better than moldboard plow? And the key to all of that is the long-term experiment that we have here at Purdue. So let me describe a little bit what this long-term experiment consists of. So this experiment is analyzing three types of tillage: no-till, chisel, and moldboard plow, as I described before, and it does it under three different crop rotation scenarios: corn rotated with soybean, continuous corn, and then continuous soybean. So take, for example, corn in any given year. So we will have, so the corn-soybean rotation, there's actually two plots, one that started with corn and one that started with soybean 40 years ago. And so in each year, one plot will be producing corn, and then the other plot will be producing soybean. So for example, if you think about observations of, say, corn yields in one particular year, what we have is an observation of corn yield under no-till, and then one under chisel, and one under moldboard plow. But of course, when you think about it, there's one observation that is coming from a corn in rotation with soybean, and then another one from the continuous corn system. So basically, we have two observations for corn under each type of tillage practice. So two for no-till, two for chisel, and two for moldboard plow, which means that we have 6 observations for corn per year, and the same for soybean. 2 observations under no-till, 2 observations under chisel, and 2 observations of soybean under moldboard plow. And remember, 1 observation is coming from the system in rotation, and the other observation is coming from the continuous system. So we have a total of 6 observations per crop per year for 39 years. Actually, the experiment had been going on for 40 years now, but there's 1 year where we had severe damage from hail, and so the data is not usable. So we dropped that observation and we used 39 years. So we have a total of 234 observations per crop that we will use to estimate yield functions. So we use 234 observations to estimate the corn yield function and 234 observations to estimate the soybean yield function. And remember, to estimate, to try to determine or quantify how tillage, how weather shapes the yield response to alternative tillage practices, we need observations on crop yields. That's the left-hand side variable in the regression equation. And then, of course, we need observations on the tillage practice, which, of course, we have, and weather. And we do have weather observations for the entire period of the experiment from 1975 to 2014, because the people in charge of the experiment have actually recorded weather observations there from a weather station. So we have all of the information that we need to estimate these yield functions. We have the crop yield observation, we have the weather observation, we have the tillage practice observation, and we have the crop rotation observation as well. Other data included in the estimation are planting date, which we observe and know in each year, and in a combination of just different variables that I will discuss in more detail when we discuss the results of the yield estimation. So we know that we need to include weather, of course, in this yield function. As we said, we're going to include it in combination with tillage practices to understand how weather shapes those yield responses to tillage. But the key here is how to include weather information into the crop yield estimation. It's not as obvious as it seems, because what the agronomic literature suggests is that really what determines yield responses to tillage practices is beginning of the season weather more than growing season weather. So, for example, conservation tillage plots tend to perform better when weather at the beginning of the season is very warm and dry, but they tend to perform worse when weather at the beginning of the season is cool and wet. Now, weather over the growing season, after the initial stages of crop development have passed, are evidence suggests that are not really that important in explaining yield differences. And so what we will do is we'll concentrate our attention. We will include all of the weather information in the yield function, but we will interact, and by interact I mean multiply weather times the tillage variable, only April weather with the tillage variable. And basically the implicit assumption there, or the operating assumption, is that really weather at the beginning of the growing season is what determines yield differentials in yield response to tillage practices, and not growing season weather. We have tried to define beginning of the season weather in different ways. We've tried the April weather variable. We've also tried April and May. We've tried March, April, and May. And I am happy to report that all of our results are highly robust to the definition of beginning of the season. So really, if you use March, April, and May, or April and May, or even different bi-weekly sub-periods of those, we've tried different ones, results are essentially the same, or at least conceptually the same, and they can vary quantitatively a little bit, but not that much. So here are the variables that we're including in the yield regression, and then the expected outcomes. And by expected outcomes, we mean how do we think these variables will impact yield. So we include a year time trend, and we expect that time trend to be positive. This is because there are slight changes in management practices and hybrid seeds used in the experiment that tend to increase crop yield. So we have included time trend to capture those effects. We also have what we call a dummy variable for conservation tillage. For those of you not necessarily familiar with the dummy variable, is basically we have for the no-till dummy, 0 when the farmer is doing either chisel or moldboard plow, and equal to 1 when the farmer is actually doing no-till. When the farmer is doing production under no-till. The same for chisel till, and then we have what we call the baseline scenario, which is the moldboard plow scenario. So what we expect is that conservation tillage will have a negative impact on yield. So basically, on average, conservation tillage tends to result in lower yields than moldboard plow. That's a hypothesis, right? So it's something that we will test once we estimate the yield function. And then we have a positive expected effect for rotation. So as we know, corn under a continuous system tends to result in lower yields at corn rotated with soybean, and the same for soybean. And so we expect a positive effect of rotation as opposed to a continuous system. And then we have what we call an interaction term between conservation tillage dummies and rotation. And we expect this to be positive for corn, maybe for soybean as well, but we don't have a strong prior expectation of soybean. But what the positive effect for corn basically reveals is that, so imagine a continuous corn system. If you do continuous corn under no-till, there's a lot of residue accumulated on the soil over time, and so that tends to hinder early development of the plant and reduce yields. And so we would expect that when somebody's doing conservation tillage, rotating corn with soybean will reduce the amount of residue on the soil and benefit yields. And so that's why we expect the positive effect of corn particularly. The most important part of the analysis, let me discuss growing season weather and then planting dates, and then I'll go back to the interactions between tillage and weather, which is where we're going to focus our attention. So for growing season weather, we include 3 weather variables in the analysis: precipitation, growing degree days, and stress degree days. Precipitation is just basically rainfall in millimeters, accumulated rainfall in millimeters over the growing season. GDD, or actually by month. So we have monthly rainfall observations, but we aggregate them for the growing season period between May and September. The same thing for GDD. For those of you not necessarily familiar with GDD, this is growing degree days, and it's basically the sum of degrees above 10 centigrade and below 38 centigrade. And that's because agronomically speaking, everything above 10 degrees centigrade does actually improve plant growth, and everything above 38 might actually hinder growth. And so everything between 10 and 38 benefits the plant, and so it's included in this GDD. And then we have stress degree days, where these are, again, the sum of degrees above 38. So we would expect a negative impact of stress degree days on crop yields, basically excess heat. We expect a positive impact of GDD, and then we expect a positive impact of precipitation for certain values, and then a -1 in case you have excess precipitation, so excess water. Then we have information on planting dates that is also included in the yield function. And what I would like to focus on is this interaction between tillage and weather. So what we've done is we have included, we have multiplied on the right-hand side of the regression the tillage dummy with April weather, and by weather we mean GDD, precipitation, and stress degree days. Of course, we don't have positive observations on stress degree days in April. That's incredibly uncommon and actually hasn't happened over the period of the experiment. But we do have precipitation in GDD, and so what this what the coefficient of this interaction terms is actually capturing is whether more rainfall does harm the performance of conservation tillage relative to conventional till, and whether more temperature does favor the performance of conservation tillage relative to moldboard plow. And we include a quadratic term of whether to capture, in the case of extreme heat or extreme rainfall, how crops are responding under different tillage practices. So basically to include potential nonlinear effects of these weather variables. I know this is an overwhelming table. I just want to focus on two things. So first, this interaction between precipitation and the dummy, the conservation tillage dummy. So we have the two practices, the no-till and chisel. We have a positive coefficients for the linear terms and negative coefficients for the quadratic term, and then we have the same for the combination, the interaction between temperature, or GDD specifically, and conservation tillage. Basically what this results mean is that it confirms our prior expectations. It does confirm the fact, the sign and the magnitude of these coefficients. It confirms our expectation that conservation tillage performs better under warm and dry conditions. And this is particularly true for no-till. So no-till performs even better than chisel when weather is particularly warm and particularly dry. And that's all I would like to discuss about that table. All of the other variables actually also have the kind of the expected effects, but I just wanted to focus the discussion in the interaction terms because that's where it's going to drive the economic analysis. So we combine that yield response, the estimated yield response information with information on expense savings from the experiment. So basically this is cost savings from conservation tillage. So remember, conservation tillage implies less operations, which is associated with lower expenses on equipment, labor, fuel, and the like. We have actually in our paper, and if you want me to share that information with you, I can show you the breakdown of this cost savings in more detail. But there's cost savings associated with conservation tillage relative to moldboard plow. That's the main message here. And then we have our assumptions in terms of crop price for both corn and soybean. We're trying to use prices that have been relatively common for the last couple of years. Okay, so here's the first result of our analysis, and I will spend some time to try to explain this here. So what you're seeing in this graph is what we call a probability distribution of no-till relative to chisel. So this curve, the height of this curve and the y-axis, that's probability, and the x-axis is the profit under no-till minus the profit under chisel. So to give you an example of how to interpret this probability curve, probability distribution curve, focus on the $5 value. So that is basically that no-till results in a profit per acre that is $5 higher than the profit under chisel. So if you go up on the $5 line here, all the way up to the distribution curve, the probability distribution curve, and then you look at the y-axis at that level, that's probably about 85%. So what that means is that there's an 85% chance that no-till will result in a profit $5 or less higher than chisel. The other way to see this, or a more simple way to see this, is basically there's a 15% chance that that chisel tillage will result in a profit that is $5 or higher than no-till. So let's concentrate on the zero value here, which is this black line, the right black line that you see in the graph. So the probability there is about 77%. And what that value implies is that no-till is simply 77% likely to perform worse, to result in a lower profit than chisel. And conversely, chisel is 23% likely to result in lower profit than no-till. So for the most part, what this graph shows is that under current weather conditions, and for corn in rotation, which is this example, chisel is 77% likely to perform better than no-till, and so it's more economically attractive than no-till. What this other line means is basically what it implies is that we would have to pay an $8 per acre subsidy to the farmer to induce the farmer to potentially adopt no-till. So basically, it could be more than that, but what that aid means is that we would have to pay the farmer $8 per acre to make no-till 50-50 with chisel. So basically, to make no-till 50% likely to result in a higher profit than chisel, and 50% likely to result in lower profit than chisel. So that's the $8 subsidy here. So we repeat this exercise for all of our crops and all of our tillage combinations. So as you can imagine, we have corn in rotation, and you can compare no-till with chisel, chisel with moldboard plow, and no-till with moldboard plow. So that gives you 4 pairwise comparisons for corn in rotation, and then you have 4 pairwise comparisons for continuous corn, then 4 with for soybean in rotation, and then 4 for continuous soybean. It is hard to summarize all of the results, and we have all of the figures in the paper that came out of this analysis, but I think a good way to summarize the results is this. It's basically what will be the subsidy that will make no-till or a particular type of conservation tillage practice 50% at least 50% likely to perform better than the conventional tillage alternative. So for example, if you concentrate in the first box here to the left, we have corn in rotation, and this 8 means that we would have to pay $8 per acre to the farmer adopting no-till to make no-till 50% likely to perform better than chisel. This is what we just saw in the previous slide. The other two, the comparison between no-till and moldboard, we don't have to pay any subsidy. So no-till is already more than 50% likely to perform better than moldboard plow under current weather conditions, and chisel is also more than 50% likely to perform better than moldboard plow with corn in rotation. So basically, we would have to pay a subsidy if we want the farmer under the experiment conditions to go from chisel to no-till, but we wouldn't have to pay the farmer to go from moldboard plow to no-till or to go from moldboard plow to chisel, because those are already more economically attractive under current conditions. The story is very different with continuous corn, though. So with continuous corn, moldboard plow tends to perform much better than both chisel and no-till. And so what this number shows is that we would have to pay $50 per acre to make no-till at least 50% likely to perform better than chisel, and $56 per acre to make no-till at least 50% likely to perform better than moldboard plow, and then $6 per acre if we want to make chisel at least 50% likely to perform better than moldboard plow. So what we're seeing here is that no-till, it's far from competitive with moldboard plow under continuous corn, and also far from competitive with chisel under continuous corn. And chisel, it's close to being competitive with moldboard plow under continuous corn, but still we would need a subsidy to induce a farmer to adopt chisel as opposed to moldboard plow if that farmer is growing corn continuously. And then for rotation soybean, what this green column, this green box reveals is that actually conservation tillage, and in particular no-till, already performs very well under current weather conditions relative to moldboard plow. This is no surprise. Most of the people that have looked at the agronomy literature or are familiar with this topic know that conservation tillage works very well with soybean, both in rotation and continuous. So no surprise there. Now, all of these results are under current weather conditions. And what we're going to do now is use our estimated yield responses to simulate future weather conditions and rerun the entire analysis. So these boxes that you're seeing here in terms of what subsidies are required to make conservation tillage at least 50% likely to perform better than conventional till, we're going to repeat that analysis, but instead of under current weather conditions, under projected future weather conditions. And I'm not going to go into the details of our data set here, but basically we use the IPCC data made available by the coupled model intercomparison project, where they have 16 different models and 11 that coming from 11 different climate groups. So we basically take random weather draws for the period between 2030 and 2069. So 39 years, the same that we had for the past 39 years. So the time length are the same. We wanted to keep it consistent. So we will take daily maximum and minimum temperature and precipitation data from these 16 different models, and eventually we put together what we call a probability distribution of projected weather patterns. And we do that under two different greenhouse gas scenarios. One sort of low, the RCP 2.6, that's the low emission scenario, and then the RCP 8.5, which is under a high emission scenario. Those two scenarios are generated based on pretty much what countries do about climate change. So if the 8.5 is business as usual. So if countries don't do anything about reducing emissions of greenhouse gases, then you end up with RCP 8.5. But if countries do implement GHG curbing policies, you end up with RCP 2.6. So these are the probability distributions of April precipitation and April GDD before and after climate change. And what we need to know here is that in terms of precipitation, for the coordinates where we have the experiment in Indiana, precipitation is expected to increase on average, and the standard deviation of precipitation is expected to decrease on average. For temperature, though, the average is expected to increase, but also standard deviation is expected to increase. So basically what this projections show is that for, at least in the location where the Indiana experiment is, the Purdue experiment is, weather is expected to become warmer and wetter on average. But also there seems to be more standard deviation or more volatility in temperature, which means that we are likely to have more frequent heat stress events, and also more frequent very low temperature events. And these are the numbers. So in inches, precipitation is expected to go from 3.6 to 4 and to 4.2, depending on the on average, depending on the emission scenario. And then GDD is expected to go from 200 to 260 in the 2.6 and 290 in the 8.6 in April. As you can see, the increase in temperature is much larger than the increase in precipitation. So if despite the fact that precipitations are expected to increase on average, that increase is not as large in magnitude as the expected increase in temperature. So once we incorporate that into the analysis and rerun the entire analysis based on projected weather conditions instead of current weather conditions, we can recover the same probability distributions that you saw for corn in rotation under current weather. We can do it for corn in rotation under future weather, corn under continuous corn under current future weather, and then also soybean in rotation under future weather. So this numbers that you see here, the 8 is the number that you saw before. So what was the subsidy required to make no-till, at least 50% likely to perform better than chisel? You have the arrow, and then the second number, the 0 here, is the subsidy, the exact same subsidy, but under future weather conditions for the 2.6 RCP, so basically low emissions, and then under future weather conditions under high emissions. So this number, this change from 8 to 0, it's a very, very relevant result, because what it shows is that under future weather conditions, no-till is more than 50% likely to perform better than chisel without a subsidy. There's no subsidy needed to make no-till more than 50% likely to perform better than chisel. So basically what this means is that projected climate change will improve the economics of conservation tillage, of no-till, to the point of making it more likely to be, making it more than 50% likely to be more profitable than chisel. So in fact, expected climate change may induce by itself adoption of no-till. It basically may be sufficient to induce farmers to go from chisel to no-till when they're doing rotation corn. Now, as you can see, these numbers go down in continuous corn as well, but they're not zero. They're still positive. So what this second box under continuous corn suggests is that projected climate change will also favor conservation tillage under continuous corn, but not enough to make that subsidy zero. So under continuous corn, moldboard plow will still be more economically attractive than conservation tillage, but it's not going to be so much more attractive than conservation tillage. So the subsidy required to induce the farmer to switch from moldboard plow to conservation tillage will go down with climate change, but it's not going to make it zero. So we're still going to need some subsidy to convince the farmer to switch to conservation tillage under continuous corn. And under rotation soybean, it's pretty much the same scenario. Conservation tillage is more attractive than moldboard plow under current weather conditions, and that's still going to be true under future weather conditions. So in general, and to wrap up this presentation, the main take-home message here is that currently, when corn is grown in rotation with soybean, chisel is preferred to no-till in terms of the probability of resulting in higher profits, and no-till is preferred to moldboard plow. When corn is grown in a continuous system, moldboard is preferred to chisel, and chisel is preferred to no-till. But projected climate change is expected to actually change some of those rankings. So in fact, for corn in rotation, no-till will become preferable to chisel under projected climate change, and chisel will continue to be preferred to moldboard plow. Now, under continuous corn, the ranking will not be changed by climate change, but the magnitude of the subsidy required to induce adoption of conservation tillage will go down. So in general, climate change will favor the economics of conservation tillage. And this is important because it means, as we said before, that then climate change will potentially be negatively correlated, at least in some places similar to the ones where we did the experiment here at Purdue. Climate change may be negatively correlated with water pollution. So an intensification of climate change by making the economics of conservation tillage more attractive may induce higher adoption of these practices, and this could in turn result in a reduction in water pollution. Now, I want to be absolutely upfront here in terms of the limitations of our study, and there are many of them. I think our study does make a substantial contribution to the literature because it's the first time that we've actually quantified how weather shapes the responses of a crop yield to alternative tillage practices, and that in turn allows us to simulate the effects of climate change on the economics of conservation tillage. I think that's a very important contribution, but we have to be very careful because this has been done based on data in one experiment in Indiana under very specific conditions. So we have to be very careful about not extrapolating these results to other areas of the Corn Belt, like the Western Corn Belt, or even Iowa or Illinois, where certain areas might actually be very different in terms of agroclimatic conditions, from the ones relative to the ones that we observed here in our experiment. We don't have, so what, as I'm sure you've noticed, we have discussed subsidies that will make conservation tillage at least 50% likely to perform better than, say, mower plow. But that doesn't mean that when a conservation tillage is at least 50% likely to perform better, it doesn't mean that the farmer will take the plunge and adopt conservation tillage. Farmers, especially if they're risk averse, they tend not to switch management practice until they see a very high probability that the new practice will perform better than the previous one. And so 50% may not be a good measure of behavioral changes. If we go and actually we have conducted the same analysis in terms of what will be the subsidy that will make conservation tillage 75% likely to perform better than mower plow, and those subsidies increase substantially. And so we need to keep that in mind as well. And the one thing that we haven't considered in our analysis too is extreme weather events, which are likely to happen with a higher frequency in the future due to climate change. So for example, conservation tillage may perform better, or the difference between conservation tillage and mower plow could be larger when extreme heat events happen in April. Now, we haven't observed much of that in the past, but if temperature increases are substantial enough, that could start happening in April, and then that could favor the economics of conservation tillage even more. So we need to incorporate, it will be ideal to incorporate those kinds of effects in here, but unfortunately we can't because we don't have historical data to quantify those effects, and that precludes us from estimating or considering these factors. So with that, I would like to open the conversation for questions and discussion. Thank you very much.
Thank you, Dr. Sesmero. For the question period, I would turn facilitation over to Laura Edwards.
All right, thanks, Hans, and thanks, Dr. Sesmero, for a great presentation. That was really great information that I had not seen before. While we're doing the Q&A and answering questions, there is a poll question that may have just showed up. Please, we ask you to respond. That part of that is for our project and who we're trying to, and the answers we're trying to get at for our project for the grant. And there'll be a couple others forthcoming. I don't see any questions in the chat or the Q&A right now, but I have a question. In that, do you assume there's a kind of an instantaneous payoff in converting to some of these tillage practices, or do you have like a period of time where that payout doesn't occur while the land adapts to the new practice?
That's a very good question, and unfortunately one that we don't have enough data to answer, because the experiment at Purdue was designed as a split plot where we have 12 plots, and once one plot is under one particular tillage practice, it doesn't change. And so unfortunately we don't have information to quantify what would happen in a plot where you go from one practice to another. We're just basically providing information for a situation where there has been a tillage practice in one particular plot for a long time. So all of our conclusions apply to, if you go, for example, from say mower plow to conservation tillage, this would apply to your profits under mower plow after mower plow has been used for a while, and then your profits under the new conservation tillage practice after that practice has been applied for a while. But we don't have information on that transition. I think that's actually something that would be very important to quantify, but unfortunately we can't based on the experiment here.
All right, thank you. We're still open for questions in the chat box or Q&A if there are any from the audience. Juan, are there any plans to expand this research into other areas of the Corn Belt?
We would really like to do it. Unfortunately, we are not aware at this point of similar experiments in other places, though if you are aware of them, we would, so the methodology here is it can be easily replicated to any other conditions. The only requirement is that the experiment is long enough to give you a reasonable data set to estimate yield functions. But the methodology, it can be perfectly replicated in any other area. So if we are aware, which we are not at this point, of experiments similar to this where you have different, plots under different tillage practices and different crop rotations for a relatively long period of time, say at least 15 years or 20, we will be happy to replicate the analysis to those as well.
Okay, thank you.
One direction that we were starting to explore actually at this point is to focus the analysis a little bit more on the economics of irrigation adoption, because we can and have actually quantified the effects of different levels of precipitation on yield under different tillage practices. And so one thing that we can learn is if conservation tillage is a complement or a substitute to irrigation. So basically, if crop yields respond better, actually our evidence suggests otherwise. So for example, our evidence suggests that yields under conservation tillage tend to be lower when rainfall is very abundant. So and tend to perform better when rainfall is scarce. So in that case, if a farmer adopts irrigation, say for example, which has been happening a lot more frequently in the last 7 or 8 years, if a farmer adopts irrigation, he's probably less likely to adopt conservation tillage, and that's something that that we would like to also quantify based on our analysis. So that's the next direction in which we're taking this.
All right, yeah, that's a great point. It's a great point. We do have a question in the Q&A from Nathan Mueller, I believe in Nebraska, and he asks, can the value of eroded soil and nutrient loss to long-term productivity be added somehow?
Yes, we are using USDA estimates to do that. Unfortunately, so what we've done with our experiment is we have run the same yield estimation under different sub-periods of this 40 years to try to determine whether a particular tillage practice tends to have long-term effects on soil productivity. We have not seen any statistically significant differences just from tillage practice, but that's something that yes, I think it will be very important to quantify. Although we have not, we've not been able to detect based on our data in terms specifically of the value of the soil lost. So the private part is the productivity. We have not detected any big differences there. The social part, though, which is the damage associated with that soil erosion, yes, we have taken those, and I couldn't give you a number right now, and I don't have it with me, but we've taken those and just basically multiply them by the USDA estimate per ton of soil, and it was, of course, over the long term, very, very significant.
Okay, great, thanks. Hopefully, Nathan, that answered your question for you. Great, he says yes. We're just about at 2 o'clock Central. Hans, do you have anything to add? Juan, I'd like to thank you again for your presentation today. I think it was very, very great information, and